Hello, everybody, and welcome to this month's Specify and Practice Community Group. Before we get started with today's call, with that, I do want to hand it over to Dave and Lewis to get started with today's call. So, Dave and Lewis, over to you.
Well, thanks, Matt. And today, folks, what we want to do, the goal of today has got to be make Lewis talk as much as is possible because he's struggling with his voice. So we'll torture him today. So today I'm coming to you from beautiful downtown New York City, sitting in one of our clients' offices. They were gracious enough to give me this great conference space to present the webinar today until our project meeting gets started. So, Lewis?
I'm coming to you from beautiful Hermitage, Tennessee, a suburb of Nashville. I'm in my second floor spare bedroom that I use for an office. And today we're going to talk about air, water, and vapor barrier membranes. And I selected the title, Oh, the Dreadful Wind and the Rain. That's an old English song that's rather lugubriously sorrowful. It's about a couple of sisters. They're both in love with the same guy. One sister pushes the other one in the river. She drowns. She's fished out. Her body is fished out by a miller who takes her hair and makes fiddle strings out of it, takes her finger bones and makes tuning pegs, and uses her breastbone as part of the construction of a fiddle. But the only song that fiddle would play is, Oh, the Dreadful Wind and Rain. We were going to play a couple of short parts from that, but Matt said we'd get into all kinds of copyright trouble. So
okay, so you just sing it instead. There we go. Yeah.
So I invite you to search for that on YouTube, and you'll actually find a wonderful recording by Jerry Garcia of the Grateful Dead playing with his bluegrass buddy David Grissman.
Well, that's interesting, especially, Grateful Dead, and here we have, Oh, the Dreadful Wind and Rain. Okay, so there's got to be a connection in there somewhere.
I think the whole band actually recorded it at one point, but the duet with Dog Grissman is especially worth listening to. I have it on a CD.
Okay, so Lewis, you've got to start into this presentation lest we not get through it in time.
Okay, well, we get to be a little philosophical today. So, David, what's the function of a wall? What's the purpose, the meaning?
The meaning of wall? Wow. Okay, yes. It has a couple of functions, but seeing how we're talking about water and air today, I think we'll limit some of those functions. We won't talk about all the structural capacity. So really, we're trying to separate inside from outside. So keeping wind out, keeping rain out, providing that thermal barrier. And whether it's infiltration, exfiltration, keeping the air from moving through the wall and causing some difficulty with the interior environment, it's really about doing these separations, interior to exterior. We could add a whole bunch of other things here, but not related to wind, air, and water.
There's also the psychological separation too, but the exfiltration, infiltration is becoming more and more important. And a couple of years ago, I did a forensic investigation of a building that had very high energy costs, and I found that there were a number of joints as you went around the building. This was during the summertime, and I could feel cold air from the building coming out through these joints and through the opening around the hose bib and that sort of thing. So it's very important in terms of controlling energy cost to not try to condition the outside air and to keep that conditioned air inside, whether it's heated or cooled. And so that's why we're increasingly concerned about exfiltration and infiltration.
And just because you have leaks in the building doesn't necessarily mean it's a wall-related problem either. So one of the stories I like is a local facilities person in Philadelphia in charge of a hospital, nationally known hospital there. When he moved into the position, he had literally thousands of leaks. So he started cataloging all of them. His number one source of leaks was dielectric unions in the piping system.
Interesting. Oh yeah, we've all been out on the job site and seen stains in the acoustical ceiling panels that are not the result of roof leaks, but are just condensation dripping from a duct or a pipe. So traditional wall designs usually kind of centered around two things. The first one is more basically masonry walls, where we tried to exclude the water as much as possible. And they were secondarily a reservoir wall, because if you have a brick wall that's 12 inches thick, you're probably never going to get water all the way through to the plaster on the inside, but you can absorb quite a lot of moisture in that thickness, and then when the sun comes out, it will dry back out. And of course, the traditional and most common form of the water shedding walls are the clapboard on houses, where you can get rain that could blow up underneath the lower edge of the clapboard, but there was a way to allow that water to drain back out and to dry out once it had it. So the water shedding versus a total barrier.
So what are you saying here? We should hearken back to some of these traditional wall designs, Louis? You know, we should go back into the 15th, 16th century and adopt some of the building techniques we used then?
Well, no, for one thing, we can't do that now that in most areas of the country we're required to have continuous insulation on the outside of frame walls. So we no longer have those options, and that's what we're going to talk about, is how do we deal with treating that water now that we have lightweight cladding systems and other systems that that are not traditional. So the concept of the masonry cavity wall is not all that old. It's maybe from the late 50s or early 60s, where we separated the brick veneer from the CMU backup. So we had a cavity drainage, and we would put bituminous damp proofing on there that is a water shedding material. It's not water tight, but it is water shedding. It's not waterproofing. And then sometime later in the 60s and 70s, we began putting insulation into that cavity drainage. And now we have lightweight cladding, such as ACM and terracotta and other metal skin systems that have drainage cavities. So again, in both of these cases, the actual skin of the building is more water shedding, but we know a certain amount of water is always going to get behind that water shedding face, and we need to have a drainage canopy for it. And then finally, we have the rain screen concept. Now, a lot of people think about a typical ACM wall as being rain screen, but it's not necessarily, because technically, in the rain screen concept, whether it's masonry or lightweight cladding, you actually have to divide the wall into airtight compartments so that it's not completely open. But the idea is that the rain screen concept is that the area, when the wind blows, that the area behind the cladding, or veneer, is allowed to equalize with pressure on the outside. Because if the pressure on the inside of the building is lower than the pressure on the outside, the wall will try to suck air through any little joint or crack, just like sucking a soda pop through a straw.
Soda pop, we know what portion of the country you're from now. Okay, so I like the analogy. So the rain screen, though, is that you were trying to describe is we have some folks making a distinction between rain screen and pressure equalized rain screen. So the kind that you were talking about is a pressure equalized, where you do try to create the same pressure outside the cladding as inside the cavity space. So if there's no pressure difference, there's no way to push the water through past that outermost rain screen, right, and into the cavity. Although it's never going to be perfect.
No, and one of the things that is sometimes done is to put vents in the brick veneer at the top of the wall as well as weeps at the bottom, so that the air can circulate, and again, it makes it easier for the pressure equalization to prevent that suction coming, because it's the unequal pressure, and we're going to see that with vapor. The pressure always wants to go from high pressure to low pressure.
So that brings up one other question, though. If we're talking about a cavity in the traditional masonry cavity with veneer brick, backup, whatever the backup material is, you actually had an airspace, and that when you were doing thermal calculations, that used to be considered a still airspace and actually worth some thermal value.
Yes.
But with the concept today, the air in that cavity is really moving air, and if it is moving, the thermal capacity of that air is significantly reduced and may not be able to be counted.
Of course, it never was more than about R1 anyway. So David.
Yes, but that could allow you to count the brick too.
That's true, absolutely. So what does the code require these days, David?
You want me to recite the entire code? Okay. So the code, and I've inserted some of the actual code references here if anybody is inclined to go and look this up. But the code requires that we provide a way to keep the water out of the exterior wall assembly and to protect the interior, especially any materials that may be subject to decay or rot if exposed to water. And it's also trying to require us to control the air and the vapor passing through the exterior wall. So the IECC, the energy code, is actually the one that's responsible for requiring the air barrier. And the building code is the one that's actually responsible for requiring vapor barriers, but only in certain climate zones. So we get up to climate zone 4, sort of equal heating and cooling days. It's optional, but getting into climate zone 5 and greater, vapor barriers become mandatory.
And even in the southern hot, humid climates like the Gulf Coast and southern Florida and Galveston and Houston, where you have the bulk of the year are cooling days, and you have a very high humidity outside, the vapor drive, there's an actual pressure that can be measured, is going to try to drive that moisture through the wall towards the inside of the building and into the wall construction itself. And of course, what happens when that water vapor or condensation hits a point where it becomes condensation, then it may condense in the stud cavity, so it's attacking the wood studs. That liquid moisture now can attack corrode the steel studs, and if it condenses inside fiberglass insulation, all of a sudden your R value drops because the moisture will conduct temperature much better than the dry product. So the R value is down.
Right, and you may actually turn the insulation into a sponge.
Yes. So, and then just fairly recently, I think it was the 2012 edition, or maybe it was later, the air barriers have now been included in the requirement for NFPA 285 testing, even though they're very thin and the amount of fuel contributed by something that's only 8 to 30 mils thick is kind of, to my mind, a little questionable. It still, that's now one of the requirements, is that in the wall assembly, now the whole wall has to pass it, that the air barrier membrane, air and water membrane, has to pass the NFPA 285 testing.
Right. So that is true for the 2012 code, where the air barrier, the weather barrier, was added to the requirement. Under 2015, there are actually some exceptions, where if you look at that carefully, you may be able to exclude a combustible air barrier.
Okay. That was a very controversial ruling, and there were a lot of people that just thought that the amount of fuel that contributed by that thin membrane was not significant. So that's interesting. I'll have to check. I haven't checked out the 2015 code. I'll have to check and do that. So, controlling the liquid water, vapor, and air movement.
Yeah, so how are we best going to do that?
Okay, we have to think about, where is the drainage plane? Are we relying completely on face-sealed ACM that we think can be made 100% perfect? Or are we more realistic and say, well, even if the face sealing is absolutely complete, we still have an air cavity behind whatever kind of cladding we have, and it's possible that in fact probable that at some point that airspace is going to be below the dew point and liquid water will form. So where's the drainage plane?
Right, and if you're relying on a barrier system, eventually the gaskets are going to shrink, the sealant is going to age, and water is probably going to get in.
Yes. As I used to tell some of the younger designers in the firms that I've worked for, I reminded them what's in the bottom of a submarine. It's a bilge. And if you can't make a submarine that's absolutely 100% watertight, what makes you think you can do a building skin that's 100% guaranteed permanent watertight? And then we have to ask, where is the dew point? The dew point being that where the temperature and the gradient in the wall from cold outside to warm inside, or vice versa. At some point, there's a place where the temperature is such that water vapor will condense into liquid water on surfaces.
Well, and dew point is relatively easy to calculate. You can do it both mathematically and you can do it graphically. So if you draw a section through the exterior wall and plot 2 points, one on the outside temperature, and the inside temperature, make them some difference apart, then you can plot by R value through each material the actual surface temperatures through that wall, and then calculate or graphically show the dew point. But that's not always a true representation, and now we have software to simulate the wetting, drying, and dew point position within the wall. One of the most popular probably is Woofy, relatively expensive piece of software to use, but many of the manufacturers selling insulation are able to help and provide Woofy analysis essentially at no cost.
And I can't help but think that part of the drive to have continuous insulation is to control that dew point location. Because when we push the insulation towards the outside of the building, it's less likely for that dew point to fall in a vulnerable spot within the wall.
Okay, so Louis, we have a question from Gail Ann Goldstead.
Oh, yes.
Asking, what do you think about just using continuous insulation, supposedly with an integral weather barrier, and skip the glass mat sheathing?
Actually, we're going to be talking about that a little bit later in the program, Gail, and I'm glad that you brought that up. We will try to answer that question at that time.
Okay, I'm going to hold you to it. And Gail, when you see that we get there, if he hasn't answered it, make sure you say something.
Absolutely. All
right.
Good point. So let's see, David, you added this third bullet point.
Well, and it's something to keep in mind. You know, what direction is the vapor pressure? Mainly because we've done some ice rink facilities where inside temperature is usually less than outside temperature. Or if you're doing refrigerated facilities like food storage or even freezer facilities, the vapor pressure is always warm to cold. So in those kinds of cases, like the ice rink, you need to treat the exterior envelope of the building what would be in reverse of anything else in the area, especially if you're in a heating zone. And you mentioned earlier, Louis, you get in South Florida or along the Gulf Coast, it may also be the vapor pressure is from exterior to interior, instead of those of us north of the Mason-Dixon that see it go the other way.
And here in Nashville, we're right on the borderline. It can, in the summertime it dries one way, and in the wintertime it dries the other way. But it can be considerable. This weekend I was out of town, and the motel that my wife and I stayed in, there was a little mini refrigerator, and the freezer compartment had about 1.5 inches of frost built up. Well, that water is coming from vapor that hit the dew point and then froze. So that's where that comes from. But we have to deal with bulk water. Is the way to do that, of course, is with weeps. So that when we have a rain, most water shedding, whether you can't build a 4-inch wide of brick that will be 100% waterproof. It will shed 80, 90, 95% of the water, but a certain amount is always going to get through, and we have to have an opportunity to let it out. Again, I've done some forensic investigations just last year, as a matter of fact, last summer, on a building in a small town south of here, where they had split face concrete block as the veneer, and then a drainage cavity, and then sheathing and so forth. And they forgot to put the weeps in. So what water did get through the veneer, and we all know that concrete block will pass a lot more water than clay brick, almost had to go into the building because it couldn't escape. So always allow your water to get out.
So did you discover it by some staining on the bottom courses of the block above the flashings?
Actually, the glass below they had strip windows, and almost all the glass showed signs of glass corrosion and staining
From the mortar?
From the stuff leaching out of it. So we actually took a couple of blocks out and found what was going on. But we went around the building and there were no weeps all over. I'll have to share some of the photos sometime.
Yes.
And then for condensation, we can deal with ventilation, because metal framing is going to if you have ACM, it's mounted on these aluminum tracks, and if it's 40 degrees outside, those aluminum tracks are going to be 40 degrees, and they may be below the dew point, and you're going to get condensation in there. So the question is, how do we allow that water to get out? We do need to have weeps, but also if we have ventilation, then the air can simply dry it out. And so, of course, a lot of cladding systems now are made so that you can make the choice between face sealed or open joints. And we'll talk about that later, because that affects what kind of air and water membrane barrier that you want to purchase, that you want to specify, I should say.
Yep. So, and then the last one, the vapor control, we have down here permeability, so it's either vapor retarding or vapor permeable. We could go either way depending upon where the vapor control happens to be in the exterior wall, and considering where the dew point and the insulation also must be, because we don't want to trap the vapor in a position where it has the possibility of condensing.
Yes, and sometimes that's more of a specification issue than it is a drawing issue. I did a review of some documents about 4 or 5 years ago for a major airport construction, and the specifier, bless that person's heart, had specified a vapor retarding air and moisture membrane for the exterior of the wall on the sheathing, but had also specified foil-faced batt insulation for the interior of the wall. So you had 2 vapor barriers. That means that any water that gets in there is never going to leave.
Let's hope they have both of those barriers absolutely airtight, and then they don't have to worry about it.
Well, and of course, I've been on a number of forensic investigations of where that moisture is condensed and inside the wall, and you get some significant mold growth on the inside face of the concealed face of the drywall.
Yes. Okay. So we have,
especially if a hotel that I looked at, not one that my firm had designed, but somebody else had done, had put vinyl wall covering on the exterior walls here in, well, it was actually across the border in Mississippi, and the amount of mold was just incredible, and of course that affected the indoor air quality and the smell of the rooms.
So we have a couple more questions for you, Lewis.
Okay.
Alicia Holloway says, I have been hearing about solar vapor drive due to the sun heating a dark moisture-retaining cladding like brick. What are your thoughts on this?
Well, okay, so we have a wet brick, and if it's dark, and the sun's going to hit it, and it's going to, obviously the increased temperature is going to want to dry it out. Now the drying can go in either direction, and that's just an issue. I mean, we all have had the experience of a brief rain on a summer afternoon that's just long enough to increase the humidity and make the day a little more difficult. If we plan the wall and the products that go into it properly, I don't think it will take care of itself, in effect.
Well, I would agree with you. There could be a situation where if you had a cold exterior wall, a wet, cold brick, where you are getting solar load on that brick, it's going to try to dry the brick. But because the brick is cold and the outside surface is now being warmed by the sun, you could find that the vapor drive is from the cold back to the warm. It's always from warm to cold. So it could be driving the vapor deeper into the wall as well as drying out to the exterior.
But of course, we're talking about the air that's inside a drainage cavity, and so if we've got our true air barriers and vapor control at that point, we shouldn't be a problem. One of the things that it's not really part of our subject today, but do think about, folks, when you put a window into a wall, you need to insulate the perimeter of the window from the cold air in the drainage cavity. So,
well, and that goes to a comment that Dave Metzger just made. Controlling condensation is not only a matter of ventilation, but also incorporating thermal breaks to eliminate direct exterior to interior metal contact. So, because most of the metals are great thermal transmitters. So if you have...
Especially aluminum,
that you can get that an exterior temperature nearly at an interior surface if there is no break.
Yes, absolutely. And you'll get condensation that's very annoying to people. So that's why one of the tricks that I sometimes use is M-seal expanding tape seals. If you put those in around the perimeter and the jambs and in the sill and the head to close off to separate the aluminum window framing from the cold air in the drainage cavity, that works pretty good because it actually has an R4 per inch, I think. So.
Okay. So now that we've got water vapor everywhere in this exterior wall assembly, what are we going to do with it?
Well, we have to decide if it's serious enough to control, and as you've already pointed out, in some areas of the country, it's really, such as here in Nashville, it's kind of a non-issue. As long as the wall can dry in both directions, or when it needs to, it's not so much of an important. It's not too important. The control location, again, as you pointed out, is up north. We always, and I am an Ohioan by birth, we always put the vapor barrier on the inside of the wall. But if you're in South Florida, then we're going to want to put it on the outside of the wall. And the control class refers to their 3 classes of vapor barriers, vapor retarders, that are at different levels.
Right. So, 3 classes. Class 1 is less than 0.1 perm. Class 2 is between 0.1 and 1 perm. And class 3 is a vapor retarder that is greater than 1 perm.
Yes.
Or at 1 perm, I'm sorry.
And of course, we already talked about the issue of avoiding double barriers.
Yes.
Tommy asks, what is code required information that is required to be included on the construction documents?
That's a good question. I'm not certain. I mean, the code is going to require the air barrier, but it does not always require vapor retarder or control. So if the code is requiring a specific material, you're certainly going to have to identify, or should be identifying, where that material occurs, as either on the drawings or in the specifications.
And of course, we all know how much the building officials love to read specifications.
Some don't even want them.
Yes, I was being somewhat facetious. So according to the Department of Energy, plus or minus 40% of all the energy for cooling and heating is lost by uncontrolled air leakage, where we're trying to heat or cool the outside of the building. Now, up to half of that is through the mechanical system, so it's not all the way. The location. Yes.
I want to make a comment about this because we're going through, in some cases, heroics to try to control air infiltration, exfiltration with the air barriers. And while it may be true that 40% is lost through uncontrolled air leakage, as soon as we make our buildings airtight, essentially, then we also have to be concerned about ventilation. So though we had uncontrolled air leakage before, now we have forced mechanical ventilation. So we're not gaining back all of the 40% of the energy that might be lost through uncontrolled leakage because we still have to condition outside air that we're bringing in for ventilation.
True, absolutely true. And the code does not actually talk about air control so much in terms of where the location is in the envelope. And the last bullet there are 16 types of air control barriers listed in the code, and drywall is one of them. So is concrete.
And plywood.
And plywood. That'll stop the air dead in its tracks. It doesn't take too much to do that. As a matter of fact, the first time I heard anybody even mention air barriers was sometime in the very late 1980s or around 1990 when I was working on the specification subcommittee that oversaw the technical content for SpecTex, which was at that time written by a Canadian specifier, Wayne Watson, and he was talking about it. But they were talking about it, especially in houses, as being on the inside of the building to try to keep moisture-laden air from getting into the stud cavities, because a single unprotected electrical outlet will admit much more moisture into the wall construction than 100 square feet of wall letting water vapor go through.
Right. So one point in the code, our next to last bullet item, the code does require air control to be continuous.
It does that.
And continuous is not required just for walls. It's for the entire envelope.
Yes, so whatever we do in the walls needs to be connected securely and airtightly to the roofing and to the foundation.
Correct.
Okay. So, can we combine these control functions? We talked about controlling air, controlling liquid water, controlling water vapor. How do we do that? And somebody had the bright idea a few years ago of we could do this all with one product.
Of course we can. It's called sheet metal.
That's right. Sheet metal is not only a wonderful air barrier, but it's a good vapor barrier. Even the very best air vapor barriers are aluminum foil.
Right. So some sheet metal and a little butyl sealant, I think we've got a home run. The only thing that it doesn't take care of is the thermal.
That and punching a bunch of holes in it, which we'll talk about later too.
Well, the holes don't count, you know?
So Joe Stieberich has come up with the concept of what he calls the perfect wall, where we put the control layers between the air gap, or in many cases now, continuous insulation. That blue there is the continuous insulation. And we mount it on the sheathing, and then we can put additional insulation, if required, in the stud cavities on the inside of the building. And there he's got a water shedding cladding that rather than a true watertight one. But that will work in any climate.
Now, but if we're talking about Joe Stieberich and his perfect wall, there is no insulation in the stud space.
Yes, he prefers
everything is exterior.
Exterior. And that makes a certain amount of sense, but you can get pretty thick, and it's often not very practicable.
I think Joe Stieberich has 8 inches of foam insulation continuous on his own home. So there you go.
Interesting. Not sure how he holds the cladding up over that, but
his philosophy, at least what I've heard him present, is if you think you need 4, double it.
There is we'll have to talk about insulation another time, but
yes,
there is the law of diminishing returns with insulation.
Yes, there is.
So we can put those control layers, and that control layer we can decide whether we think we need that to be a vapor barrier or not. But it will work there in all climates.
Well, and in Stieberich's perfect wall, because the insulation is all outboard of the air barrier can always be vapor retarding.
Yes, because it allows the wall can dry in either direction. And that's the point. Unless you're using foil-faced polyiso. Well, we'll talk about it. Okay, so what are the basic materials for air and weather and water barriers? We have sheet types. The traditional one is asphaltic felts. And then we got into the synthetic polyolefin sheets, like Tyvek, and self-adhesive sheets, either bituminous or non-bituminous types.
And fluid types have been really coming on the scene. It seems like an awful lot of manufacturers are introducing the fluid types. It gives you some flexibility, especially in detailing connections to adjacent materials.
Yes, and I've go ahead.
I was going to say, and silicone, I think, was probably one of the first ones. They actually made it for a different purpose, but because silicone is vapor permeable, and because it's essentially waterproof, that it was one of the first ones on the scene, but wasn't really promoted for that particular purpose, even though it was available.
One of its advantages is silicone is totally impervious to UV. So it can be exposed on the exterior of a building indefinitely, forever. And if you have ACM cladding or a different type of cladding with open joints, silicone is probably what you ought to look at. It's more expensive than some of the other types, but it will remain undamaged for the life of the building.
But pay attention to dew point because it is vapor permeable.
But it is vapor permeable, so you have to think about that.
Yes. So two of the, I would say probably the newest one that I know of on the market is actually the STPU, the Silicone terminated polyurethane. STPE has been around a bit longer. There have been, I think there are fewer manufacturers offering STPU than there are STPE.
Yeah, I can't think right now. I can't think of a single one, but I know 3 or 4 that make the STPE.
And the acrylics were brought on too to be the vapor permeable.
But there are vapor retarding ones too.
Right, but they were the first vapor permeable in response to trying to deal with the dew point and as the antithesis to the sheet bituminous membranes.
So the Sil-L terminated stuff has to do with including some silicone parts, the terminations. I guess those are at the ends of the long chain polymer molecules, and they give it certain advantages. It does set very quickly. Well,
it gives it some of the properties of silicone without.
Yes.
And it actually allows silicone to bond better to those products.
Yes, because some silicones require a primer to get really good adhesion, as we all know from some silicone sealants. Not all, but some.
Okay.
Acrylics are, one of their problems is that their polymers are vulnerable to UV degradation, so they have to be covered, they have to be kept in the dark to have a long lifespan. But they're a little less expensive.
So they're sort of like specifiers. They have to be kept in the dark. To have a long lifespan, is that how this is going to work, Lou?
I guess. I'm working on it. I'm working on it. So, and then of course there is SPF, spray polyurethane foam. I put it in with the fluid applied types because that's the way it's applied. It's sprayed on, but of course it sets up into a solid. And there are a couple of systems that combine rigid board continuous insulation with SPF sprayed on the backside in the stud cavities. And because it's sprayed in, the thought is that it would fill any and all gaps so that you really do have a very airtight basis.
And that is one system that's being offered as the sheathing, the insulation becomes the sheathing without a separate sheathing board to try to help, who were we trying to help? Now I've lost it. Gail. Thank you. Thanks.
Gail Ann. Which brings us to the board types, and there are a couple of those. And one of them, as I say, one of the common systems is combined with spray polyurethane on the inside, on the back side of the wall, but you don't need the sheathing because you spray the SPF against the back side of the insulation board. There's another company called Smart CI that has these mounting clips that are made out of fiberglass, so they have a very low heat transmission themselves that can be used to support lightweight cladding. And they have various grooves, and they say grooved polyisocyanurate insulation that's foil faced, and they get glued into this system. And of course, the foil facing works as fine as a drainage plane, so that works. And then just recently, Georgia Pacific has come up with a special gypsum sheathing that has a special layer within it for controlling liquid water as well as, and you simply apply a liquid mastic, I should say, product to the joints and to the detailing into the rough openings of for doors and windows.
And there are other gypsum products on the market now that have been introduced where you have factory applied air barriers on the face of the gypsum or the cement sheathing boards, so that you buy the gypsum with the air barrier already applied, and then you only need to treat the joints in the field.
Steve Gantner asked a question specifically for you, David. He says, when choosing fluid applied, do you prefer thin or thick film products? And we might remind folks that if you look in the master spec section for fluid applied air and water barriers, they actually have 3 categories: thick, medium, and thin. Yeah. Rather than dividing it up by material type, they divide it up by thickness, which is interesting.
Yeah, which is interesting. So, yeah, Steve, if I give you my answer on this, I'm going to end up naming products, and I think I'd prefer not to do that. But what I tend to do is look more at the chemistry and see, because when I'm looking at it, I want a product or a system that I know that can be compatible with all of the transition materials, whether it's a sealant, whether it's a transition strip of some sort, but to know that I have a full compatible system to connect to all those penetrations that are going through the air barrier. So, and I think that there are some out there that make that really easy. So if you look at the chemistry, I try to find things that are not going to be affected by water, that don't absorb a lot of water, that hopefully remain in place, because some of the biggest fear when you think about adhered materials is, 30 years from now when we peel back the veneer, are all these materials still going to be attached? Will the adhesives actually be working 30 years from now?
Yes, and I agree with that because, like I say, cardboard makes a great air barrier, but you can't. We can't use it on buildings. It's not the thickness or the thinness that makes the difference. I concur wholeheartedly with David. It's a matter of what chemistry and the performance. And the performance. And to a certain extent, what's the budget? Are we talking about a building that may be replaced in 20 years? Or are we talking about a hospital that is going to want to be there for 50 or 60 years?
Well, and the other thing too is consider how difficult it may or may not be to install, and whether or not it's going to require a lot of detailing because of many openings or many twists and turns in the exterior envelope.
And in some cases, you may want to actually, if you have a negotiated general construction contract, you may want to talk with the contractor about how long is this thing going to be exposed to the weather before the concealing construction, the veneer, the cladding is applied to it. And that could affect what products that you decide to use. So making this decision is not an easy one. There's no one simple cure-all system that will work on every project. That, unfortunately,
I wish there were a simple answer. Then we do. We could have just started the presentation. Here's the answer. We're done.
But I hope we've given you some ideas and about what to look for and what decisions to make.
Okay, so Louis, we're almost up on the hour.
Yeah, we got to go hurry. So we do have some testing. There are some adhesion testing, which is a good thing. But again, David, and I are concerned about will that product still be on the wall some years later. We had a project in South Texas 3 or 4 years ago that had peel and stick modified bitumen, and it was behind a metal cladding, and it got so hot that part of the bitumen dripped out to the bottom on the flashing and dripped onto the roof, and wasn't overly compatible with the TPO roofing. So that's another consideration. But you can test. One of the things that would be a good idea is to perhaps test adhesion. If you're doing a mock-up assembly of the exterior wall, then there are test procedures for that, and there are procedures for doing the whole building. But obviously, we need to do that before any cladding is put on, and sometimes that's not overly practical.
And before interior finishes. So really, it's a matter of enclose the building, do the test, fix the problems, test again if necessary before we start finishing the thing out.
But that has a major cost effect on schedule, and you may get some pushback from both your owner and your contractor. But there are projects where, especially some of the government projects, are demanding that. But fortunately, there are, to help us make these decisions, there are some really good information available at the Air Barrier Association of America website. They have a quality assurance program for installers. They have suggestions for testing, sample specifications. Part of the testing that they do is there is an ASTM test for how well does the membrane seal to screws. So when we're screwing the tracks to hold on the ACM or the Z clips for the continuous insulation, and we're punching a bunch of holes through our membrane, our wonderful membrane, how well does that membrane seal to those screw holes? And there is actually a test for that, and if you get on their website, you can find a lot of the products named by name and how they've been tested. And
and they do have sample specs for all of the different classes of air barrier material. So it's not necessarily all proprietary, but by class.
Right. So, okay. Well, we actually wrapped it up.
Yes, we managed to finish, and virtually on time. Virtually on time. So, want to thank you for attending, and hope that you're able to join us again next month. And Louis and I had chatted about this. Would typically be the first Monday, which is July 6th, but that's in the middle of a very short work week because of the 4th of July holiday. So we will be moving the meeting to the following week, July 13th, the second Thursday.
So we appreciate all of your attendance. We appreciate, we respect your time and hope that what we present to you is useful and helpful. And if you have further questions, Dave and I are both available by email if you to get into some of these things maybe a little bit deeper. And we, as always, we regard this as your program, not ours. And if you have some specific topic that you'd like us to discuss, we would love to hear from you. So keep the cards and letters coming in, friends and neighbors.
And we have one of those topics picked out for July. So tune in. It might be
Oh, you do?
Yes,
oh,
I do.
good. I look forward to hearing about it.
No hints.
Okay. Well, thank you all again. And Matt, we'll turn it back over to you to wrap up.
We appreciate your time and effort. Again, Dave and Lewis, thank you for your always enjoyable hour of dialogue and knowledge as you share with us. And we look forward to seeing you all next month. Thanks, everyone. You may now disconnect.